So in this video, I'm going to go into a little bit more details of the different decays from what you watched in the last video. So let's start with the alpha decay. Recall that an alpha decay is simply a helium nucleus, so 2 protons and 2 neutrons. And so let's take a look at the decay that was done in the video. So let's say we had uranium-238 92. And that's going to decay as an alpha particle, so we're going to get 4,2 helium. So this we often refer to as the parent nucleus, and then the final, this would be our alpha particle here, and then the final particle we'd call the daughter. So if this is our parent, and we're going to lose 2 protons, 2 neutrons, we're going to go ahead and draw out the daughter. So we're just going to simply subtract here. So 92 protons minus 2 means we're now going to have 90 protons. And then 238 nucleons minus 4 nucleons means we're going to have 234 nucleons left over. And again, you look at your periodic table, you find out that's going to be thorium, and you can write it like this. Now, the mass, let's take a look at the masses of these. Okay, so the mass of uranium, look it up in a chart, it's 238.05080. The helium mass is going to be 4.0026. And then the thorium mass is going to be 234.04359. So the point is, let's look at what the combination afterwards is. When you add these two up, you're going to get 238.04619. So we started with more mass than we ended with, right? 238.05, 238.04. So we ended with less mass. So the question is, where did that extra mass go? And as we've been discussing, that extra mass now gets turned into energy. Remember, mass can turn into energy. And so the leftover mass is going to turn into energy. So again, we call this the mass defect, and you go ahead and subtract those two from each other. So the difference in masses, we're going to, when we subtract these two, we're going to get 0.00461. And again, these are in atomic mass unit. So this is now going to turn into energy. How much energy? Well, we can use our E equals mc squared. And if you want, you could do it the long way and go ahead and do all your conversions. Or if you remember the conversion, 931.5 mega electron volts per U. So 1 U is equal to 931.5. So if we multiply that by 931.5, we're going to get amount of energy is 4.29 mega electron volts. So the next question is, well, where does that end? What do we mean by energy? Where does that go? Oops, let's pull this up. 4.29 mega electron volts. So where does that energy go? Well, this goes into the 2 atoms. So this extra energy is going to then be transferred into these 2 atoms. So, for example, if you have your thorium atom, you have your helium atom, they're going to take on that energy in the form of kinetic energy. The thorium would go one way, helium would go the other way. Now, just to get some perspective, helium is much, much, much smaller than thorium, right? Imagine from last year, imagine we take a big old football player who weighs 234 pounds, right? He's huge. And you have a little kitty cat who weighs 4 pounds. And they push against each other. Push, push, right? Equal and opposite forces. Well, who's going to go faster? Who's going to go flying? Well, the cat goes flying this way, and basically the big guy barely moves. So when you see this question, they will always usually say the energy, assume that this energy goes into the helium atom. So what is the velocity of the helium if all the energy goes into the helium? Okay, so I'm just going to kind of leave this up to you to go ahead and solve it. You're essentially solving for kinetic energy, 1/2 mv squared. You do have to make some conversions into mass to solve it, but I'll leave it up to you to solve it. I'll write the answer here just so you can check your answer. You should get about 1.4 times 10 to the 7th meters per second. So next up, let's go ahead and take a look at a beta decay. And for beta, remember there's two types of beta decays. So the first type of beta decay we're going to look at is the beta minus. So remember, a beta minus is simply an electron. And the way we usually write this would be E0 negative 1. So let's take an atom. Let's go back to our thorium, 23490 thorium. And let's say it decays by beta. So that means it's going to thrust an electron outwards. Okay, and then here's what's going to happen. Well, electron is not a nucleon. So in beta decays, you will always end up with the same amount of nucleons. So it's always going to be 234. It's going to stay as 234. Here's what happens. You now created this negative charge. So in order for charge to be conserved, we need to somehow cancel out that negative. So in order for charge to conserve, we want to cancel out that negative. So the nucleus is going to become more positive. So we're going to end up with one more positive to cancel out that negative. So in other words, this is going to take on this is going to become 91. And that turns out to be PA. So anyways, what's happening here, notice the nucleons are the same. So we have essentially turned a neutron into a proton, or the word we use for this is we've transmutated a neutron into a proton. So our neutron turned into a proton. In that process, it's going to go ahead and thrust out an electron. Okay, so the math on this, again, if we were to look at this, we'd have 234.04359 starting at point for thorium, and then our palladium here is going to be 234.0430307. So again, if you look at this, we are losing energy, right? So we could say, oh, we're going to we're losing mass, which means on this side we're going to have to add some energy here. Okay, now last video didn't talk about this, but there is another piece to this, and there's another piece here which is called the anti-neutrino. Symbol looks like this. And basically this is just a very, 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 very tiny charge, small mass, and essentially it exists. We experimentally, the math wasn't working out when they first did it. So someone proposed that there was some little mini neutron that was given off. It's not a neutron, but he called it a baby neutron. And later we were able to discover it. For our purposes though, this is fine, but just to be clear, there's a little extra piece here. So let's look at the next form of beta decay. So the next form of beta decay is called beta plus, and a beta plus particle is, well, it's called a positive electron. And the positive electron is essentially the anti-electron. We all actually call it a positron. Okay, so we'd write this as E plus 1, 0. And what a positive electron is it has the same mass as an electron, but it has a positive charge. So electron normally has a negative charge, a positron has a positive charge, but the same mass of an electron. So not a proton. Protons would be much bigger, but a positron. So let's do one of these. Let's take a oxygen. So let's go 1580. Okay, notice this is an isotope of a normal oxygen. So this is going to decay by positive beta. So let's say that that's going to be E0 plus 1. Okay, so in this case, in order for this to happen, notice we now have produced this positive charge. So in order to counteract that, this needs to lose a positive charge. So in order for charge to be conserved, if this gains a positive, then this is going to have to lose a positive. So remember, in beta decay, nucleons are going to stay the same, but in this case what's going to happen is we're going to now lose a proton. And in fact, we don't lose it. What happens is a proton now turns into or transmutates into a neutron. And this would be nitrogen. And just like before, we're going to end up with another guy. This one's just a pure neutrino. The last one was the antineutrino. This is just kind of the pure neutrino here. So this is our beta plus decay. Again, if you do the math on this, I'm not going to write it down, but you're going to end up with more mass. You're going to start with more mass, less mass. So in all of these, you release energy. Okay, in all decays, this is why they happen. They're in a kind of an unstable state, and they're going to decay down naturally, and in this process we're going to release some energy. If we weren't releasing, if we had to input energy into this, then it wouldn't just naturally happen. You'd have to somehow input energy to get the reaction to happen. Alright, the last type of decay is the gamma decay. So in a gamma decay, not much happens, at least in terms of what you need to know about. So we're going to take our atom, let's say, I don't know, we'll just take a oxygen 16-8. Okay, and what happens is this nucleus is going to actually be excited. And so we usually write that just with simply an asterisk. And much like previously when we talked about excited electrons jumping up, in this case we have these nuclei moving into these higher energy levels, higher energy states. And so this often will happen in maybe a nuclear reaction. All that high energy gets released and it excites the nucleus. And so when this relaxes back down to its normal stable state, 1680, in that process it will release that extra energy. So we're starting with more energy. Instead of mass, we're talking about energy here. We end up with less energy in the oxygen, and so that extra energy gets released as a gamma particle. And the gamma particle, it's just a photon, so it's just an electromagnetic wave. It's a photon, and whatever energy is left over, it's going to turn into this. Okay, so hope that helps. Actually, I'm going to end with one final question. Let's say you have, let's go back to our uranium-238-92U. Let's say that undergoes, how about 4 alpha decays and 5 beta minus decays. Can you go ahead and figure out what the daughter nucleus is going to be? Oops, daughter. I know how to spell. What is the daughter nucleus? All right, and we'll go over that in class.